Social distribution. How is it distributed? But localization is where understanding anatomy, precisely in anatomy, understanding precisely in the anilobi, understanding precisely in the kidney, in the cortex, in the pancreas, or showing the exact location specifically in the pancreas. This is the function of CT. You create a fusion between the PET image and the CT image and benefit from the biodistribution of the activity of the substance. At the same time, you benefit from the CT image in precisely determining the location of your substance.
Well, let me ask you a quick question. Why exactly are there noticeable changes in the appearance of food before these changes occur? And then it suddenly becomes completely white. In this particular image, is that correct? Yes.
Exactly. Are there changes in food or not? Yes. Exactly. Are the changes weak or strong? Weak. Okay. Will the count that reaches the detector be a lot or a little? A lot. A lot. He will see it illuminated. That's why I didn't see it illuminated. Is that clear, doctor? Clear. So when he takes it in the CT, did it arrive or did it not? It arrived, right.
Okay, doctor, so if I have a nodule, because I had a story talking about a nodule, and there was a doctor saying it was evaluated with non-attenuation correction, this nodule was evaluated and considered positive for metastasis. Is that wrong? Of course, it's wrong. If you had the PET CT image, which is the attenuation corrected image, would that lesion be visible? Not at all.
On what basis do you rely? The non-attenuation correction cannot be relied upon. As you can see, the data it contains has very significant errors. We perform attenuation correction to correct the image. We need the best doctor to make the necessary corrections. The idea is that if there is misregistration, for example, if the breathing is not synchronized with the breathing topic, this is one of the essential aspects. If there is a breath for you, you perform fusion between the image or you perform attenuation correction. For instance, if you took a CT image and in that CT image the breathing was not synchronized, if you have a part of the liver or diaphragm in that area, what happens? A change occurs in that area, right? When the area changes, the attenuation in that area will change, revealing the photopenic area present there. If there is a lesion, it can lead to misdetection or mislocalization, whether it is on the liver or the colon. This issue is addressed today with pre-getting. There are some problems that affect the detection process for the patient with the same patient. This addresses this issue in a comprehensive manner to ensure accuracy and reliability in the results obtained from the detection process for patients with similar conditions. There are some softwares that improve brief artifact through a specific algorithm that enhances and performs correction for the existing brief artifact. Alternatively, registration can be done manually. You move the CT image and work with the PET image and ask it to do this in a certain manner. Okay. For example, in this image, there is a misregistration of about 11 millimeters between the CT and PET scans. You can see here the myocardium, which is the area of the apex. When we performed registration or corrected the existing registration, the image returned to normal and this part became hyperactive again. Okay. There are some important things in something called, what is this topic? Today, you are telling me that you are a doctor, right? You are dealing with daily quality control. In daily quality control, you will find the technician using a radioactive source. This radioactive source emits positrons or 2 gamma photons at 180 degrees. Before we start working in the morning, he must perform calibration or conduct quality control. Why quality control? he performs something called a blank image. What is this blank image? First, it ensures that all the detectors, all the rings, or all the crystals are functioning efficiently. It ensures that he creates a specific image that he uses to apply correction to the images of the patient. For example, you are using a point source. This point source emits gamma photons in all directions at 180 degrees. The crystals are located around you, and these crystals begin to create an image of this point source. Here, there is no attenuation, nothing at all, but this image is referred to as a reference. This reference tells you that the detection or the line of response is what I call the line of response. The line of response has a specific count for which detection has been performed. So what happens next is that the average of all these lines of response is taken. For example, here we have a line of response, and here another line of response, and here yet another line of response, covering all directions and angles, but each pair sums to 180. Then the average line of response is calculated. This average is divided by each line of response, count obtained in every direction for each crystal, to derive something called the correction factor. This factor acts as if it is performing normalization, which is used to correct any deviation that may occur in the detector during the imaging process. This is the function of daily quality control, or the meaning of normalization. Its role is to take a blank image for each line of responses to derive the correction factor. This correction factor is then multiplied by the counts that will be obtained later from the image, effectively unifying or standardizing the detector efficiency across the entire PET-CT. It gives you a homogeneous image, and if there is an update to the crystal or the detector during the imaging process, you need to update it. Therefore, daily quality control is very important during the imaging process for us. You should use a daily quality control test. What can you do using daily quality control? I have this germanium radioactive source. What should I do, Dr. Hani? I come every morning to first test whether everything is working well or if there is a malfunction. I need to use a radioactive source, but this radioactive material costs money. So I use this source, which has a relatively long half-life of about 2 years. This source emits 2 positrons at an angle of 180 degrees, producing 511 kilo-electron volts for each positron in this direction and in that direction. Why am I doing this? I want to check the efficiency of my detectors to see if they are all working with the same efficiency, or if there is variation among the detectors or the crystals. If there is variation, it is very likely that there will be a fluctuation, and you need to deal with the electronics. This fluctuation requires a correction factor. How do I apply the correction factor? Each line of response is present, and I have detected it. This line is what I call the line of response. What does the factor mean? For example, I took 1,000 lines, those 1,000 lines, right? Then I take the average count of the average lines. Logically, Dr. Henny, should all the average lines have the same pattern, or are they different? Logically or theoretically? No. Theoretically, like some. May God. Open your mind. So what am I doing? I'm correcting these values. So what should I do? I take the average and name each one your sterile line, meaning, for example, these 1,000 lines of response, each line gave you 100 counts, right? Okay, each line, so their average is 105. The average is 105, right? Okay, you have one line at 100, one line at 95, and one line at 110. So what do you want to do? You want to adjust these detectors so that they all become homogeneous. What does that mean? Pay attention. These different numbers will affect what, doctor? The detection efficiency has become different at different angles, right? When you come to image a patient, each detector will have different detection sensitivity, right? Is this clear so far? So you want to unify the detection efficiency. So you create a correction factor. How do you do that? You take the average you calculated, which is 100. How do you divide 100? By each value of the line of response. 100 by 110, 100 by 105, 100 by 95. What do you get in the end? You get a correction factor for each line of response in its direction. So what will you do with this correction factor in the end? You will multiply its value by the detection value you obtained from the patient as if you are correcting your ability in the investigation. Okay? Okay, Dubai. Okay. This is the area we are talking about. The concept of gamma photon detection involves many detectors and performs detection in a different location than its original position. Your image is specifically focused on the peripheral area. Of course, there are some algorithms called point spread function, which are available in Siemens and Philips. This improves the detection and enhances the resolution of the image. Here, you can see that the allegiance is more blurred and its resolution is lower, while here the image is clearer and more defined for me. There are some things that patients should preferably not exert any effort or strain to avoid increasing the uptake of radioactive material, as this can lead to artifacts and result in hyperactivity in the imaging. For example, there is hyperactivity in the pectoralis major due to exercise or high glucose levels, which affects biodistribution. There is also something called truncation. Let me explain. I have the SPECT. I take a SPECT image if I dose, and then take a PET image. The two gantries are set up like this. Here is the first gantry, and here is the second gantry. The patient enters to take the SPECT image, and then goes to take the PET image. After that, the field of view must match. Both the SPECT and PET fields of view should be equal. If the SPECT field and view are small, do you think that will affect you? Yes, it will affect you. Because at that time, you want matching between the field and view. So the pixel size should be the same size. Because when you perform attenuation correction, you will take each pixel on the site to see its attenuation. If there is a field and view that is different, and if the pixel size changes, if you used a different field and view, if the pixel size changes, if it changes on the site, 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 it is present. Did you not do this properly? Okay. All right. So how will this affect you in the end? It affects you in this. What is called this happens, folks. Why? As a result, your view is small regarding the location function, art factor. The result of your view regarding the CT is small concerning the bit. Have you heard about time of light? The idea behind time of light is that normally, if I have a setup without time of light, and if I have a setup with time of light, I have the detector, and here are the two detectors, or crystals. Each of them will receive 2 photons, and thus I determine the location of the annihilation. How do I do that? I think about the concept of bad projection. We used to say that the point where the annihilation occurs is exactly that point, right? This point will be the most significant point for me. Why? Because I will receive signals from here and from there, and I will receive from many places. So each 2 crystals will start to count the received signals and perform back projection on their track, on their line, on their path until the brightest point appears, which is the cross sections between all these lines of responses. Thus, I have determined the location of the annihilation, but this is at the level of resolution, which is not great, meaning this method was used in expect. Yes, this method is good and everything. I will determine the location for you. But if you want to achieve more accurate localization of the annihilation, what should you do? They said you should use something called time of light. What is time of light? Time of light is a technique that relies on the timing of receiving the two photon collectors coming in at 180 degrees and HRZ is that the photon here, the annihilation means that the photon that reached crystal number 1 arrived in less time than the photon that reached crystal number 2, right? Correct. So now you have a time difference between the photon that went to 1 and the photon number 2. I told you I would use this time difference to determine the difference in the location of the annihilation. Now, to avoid confusion, let's see how this works. I have a crystal here, and I have a location where something is happening. For example, let's say this location is a certain distance away. You know how far that is, right? You know that distance is 70 centimeters, 60 centimeters, or consider it as 70 centimeters. Okay, in this case, I say that this location is in my center because the time that arrived here is the same as the time that arrived here. So the difference in time here is 0. So where is the location? This location is specifically in the center. Now, if the location of the annihilation is not in the center, here, for example, at this end, let's say that, as you know, the biometric analyzer or my detection device indicates that this midpoint area is indeed exactly that. But there is a difference between the midpoint area and the area where the actual annihilation is, right? Precisely. Okay, from the midpoint area to the location of this crystal, I will call it R. From this midpoint to the location of this crystal is also R. So I have R plus X, which is R plus the distance to the location of the annihilation, and I have R minus X. R plus X is specifically the distance measured from detector 1 to the precise location of the annihilation. R and X are the distances from the detector 2 to the location of the annihilation. Did the doctors understand it, or was it a problem? In silence, okay. So this distance is a bit longer. What does the distance equal? A photon is like light. The speed of light is 388,000 kilometers per second. That is the speed of light, right? So speed equals time. Speed in time. What is this time? The time of arrival, let's say the time of arrival of the photon at detector 1 will be called T1, and the second one C in T2. All right, if you subtract these two times from each other mathematically, what will happen? The ground will shake and you will get 2x. C equals T2 minus T1, which is C times delta T, where C is the constant. What is delta T? It's the time difference. I'm sorry, delta T. Delta T is the difference in time between the arrival of the photon at detector 1 and the arrival of the photon at detector 2. Then you divide the 2 by 2. So what is LXD? LXD is the center distance for the location of annihilation. Annihilation means that at this moment, you were able to determine or confine the localization of annihilation more accurately. This is the time of life. It is the time of life that through the time difference can precisely determine the X in the localization area. Instead of taking a larger area or range for the localization, it is now more focused, allowing us to pinpoint the location of your annihilation more accurately. This is the technique of the time of light. If I have the time of light, here is an image of 60. For example, you see this legend. Here, in the case of not using, and here in the case of using, there is light with you, and it appeared in matters here. For example, this is with and this, and here it is higher, cut off here, for example, or this. With and here, it is about to be released here, for example. Liegen hop, or Liegen hop, such as without time of flight. Okay, so is it doing or improving well, or is it risky? Okay, well, all right, okay, good. There's also a point, before we move on to the topic, this image is a thyroid image, right? All the thyroids have the same appearance, but these thyroids, okay? In this image, you can see the 4 images with different appearances. You might say, no, this one is like that, meaning here the counts are high, here the counts are a bit precise, here the counts are completely absent, and here the counts are very low, okay? Well, why have the counts become weak? The whole idea is that you have a problem with the quality control of the issue. What is this problem? If we are thinking about this curve, in this specific curve, if we adjust a parameter called the window demonstrates that I want to take 20% at the photo peak area, which is 140 kV. If you move a little to the north or a little to the right, the change in the release of energy and the photon begins. In this way, it starts to change with you in, and so what does it start working with you? It begins to show up. If you are here on the off peak, on the right side, then in this case, the count will start to show up low because you will collect low intensity photons. So this image, the doctor doesn't know how to diagnose it. I mean, the doctor hasn't diagnosed it, but can't discover that there is a problem. So this artifact or error appeared as a result of what? The result is that quality control has not been done, or there is an issue with the window you want to set compared to the actual window, and no one is checking this matter. Here is the same idea. This is the kidney. The kidney here is very deep. What happens when it happens? When it happens, when it happens. When it happens, when it happens. When it happens, when it happens, when it happens in the role, in the diagnostic process. If you don't perform quality control properly, in this case, you won't discover any issues in the diagnostic application, and you will diagnose the case as completely normal. The problem itself all comes down to what? That your quality control is not accurate. In this case, you need to do a recalibration to adjust the window to 140 kilo for this phone. The same idea applies here. This is a cardiac case. Subscribe to the channel. Here, there are different peaks because, for example, in Legion, I am measuring without the color that came from another university, so the convincing transfer is called the real color. Here, here, here. Its size varies. Its size changes with the shifting that you are present. Regarding this case, everyone, it was entered with a very high person. There is the idea and there is a problem. And then you just forget about it. While this talk is really all related to quality control. For example, you are the officer. The photo peak is set at 120 kilovolts, but I will set yours at 125. Do you see the difference between the two images? What do you think of the image above? Do you see the background? The background that is dense, which is behind the heart. This is the heart. Now the background here is high. Why is the area behind it high? Because you selected energy and you didn't do the defection columns. The same idea here at 140 and you selected higher energy. Your background decreased. Your background decreased. So the image is processed like this. Therefore, the choice of the window you are working on and the selection of the photo peak at any specific energy all affect the image quality, and all of this impacts the diagnostic accuracy, whether in the build or in the space. For example, this is an image of the uniformity. find some batches appearing here. The image is supposed to come out like this June 4th and be processed in this way. The image now has batches like this, or there are cracks present. The inspection quality has broken down. If you don't perform quality control, or for example, if there is a photo multiple ratio and it gets dark, meaning you run this when you come to work and diagnose, or when you come to take images. Just look at this condition. It's very bad. Here, there is a white spot that you see on the edges. In summary, it looks bad or poor, but you can't tell how your image looks. Look at it with me. Look here. For example, I have this circle showing a hypoactivity where there is a defect in the myocardium. Here, there is a defect, a problem, and I am diagnosing that the patient has, for example, a defect that is dead in the myocardium. Meanwhile, the place where the uniformity should be is not right, so the image starts to show the background incorrectly. When I perform the recalibration, I find that the defect is no longer dead. Okay? The same applies to the center of rotation. This is an image if your center of rotation is not correct, and this is an image if your center of rotation is correct. The center of rotation is where you see the motion of walking itself, the motion of walking. Does it seem to you that the wrestle or the head is moving and keeps moving and moving and moving and moving and moving? The same idea applies. If there is a problem with the sensitivity, then the counts produced by the detection will be weak. I will see the image that you created. Here with the high counts is a quick image. Here with the closest sensitivity, here the sensitivity is much lower. Therefore, you must share the quality control for the matter. This has a very good effect on the quality of the image. Consequently, it affects the diagnostic accuracy.
Enjoy.
Don't put it in. Don't put it in. Don't put it in. Don't make a difference. Don't make a difference. Don't put it in. Don't make a difference. You see that there is